and welcome again to FlippedHarber for Algebra 2. In this video we're going to take a look at rational equations and inequalities. Our objectives for this lesson are to solve rational equations and to solve rational inequalities. The outline for this video will start by taking a look at what a rational equation is. We'll talk about something called an extraneous solution. We'll look at solving rational equations. We'll take a look at a classic rate problem, a problem that you're going to see a lot on the ACT and other standardized tests. And then we'll take a look at solving rational inequalities. So, first of all, what is a rational equation? A rational equation is basically an equation that involves a ratio, a fraction. Now, specifically, what we see in a rational equation is the variable is down here on the bottom of a fraction somewhere. So when we see a rational equation, we're generally looking for that variable in the bottom. Now, it doesn't just have to be in the bottom. We can have that variable occurring in several different spots, like we do in the second rational equation here. One of the terms has the variable in the bottom, one of the terms doesn't. We can even see that variable in several different spots in the equation, but again, the fact that we see the variable in the bottom of the equations is really what makes it a rational equation. Now, beware the extraneous solutions. An extraneous solution, if you really just look at the word extraneous, it's an extra solution that doesn't work when you plug it back in. Basically, they're answers that don't really work. They don't always happen. I'm not saying that with every rational equation you're going to have extraneous solutions, but they can really put a hamper on your day, especially on test day, if you don't plug them back in to check them. You should always check your answers with rational equations. Alright, so let's go ahead and start looking at solving a rational equation. Now, I know what keeps you up at night, what sends you screaming into the darkness is fractions. So the fact that we have a fraction right here is probably making you pretty uncomfortable. Well, let's make it so that we don't have this fraction by getting rid of it. And the way we're going to do that is we're going to multiply the whole equation by the denominator. So we're going to multiply the whole thing by our w. Now, when we do that, everything that has a w in the bottom, it's going to cancel out and we're just going to be left with the top of the fraction. Everything that doesn't have a w in the bottom is going to get multiplied by that w. We go ahead and add over the 4w. And we divide by the 11 and we have our solution. Now, maybe this solution works, maybe it doesn't. Maybe this one solution we got is an extraneous one. It's not. When you plug 1/11 back in, it does work. So this is our answer. Let's take a look at another one. Now the difference here, we see an m occurring in a couple different spots, including on the bottom of the fraction. That's why it's a rational equation. We're still going to multiply to get rid of that denominator. So again, anything that has that m in the bottom is going to cancel it away and it's not really going to get multiplied by the m. Anything that doesn't have that m in the bottom gets multiplied by that m. It does not go away. So we have to deal with that. So our m becomes an m squared, our 7 becomes a 7m. Move everything to one side and what we've got is a quadratic. We see this square here, so that means that it's a quadratic. So that means I'm going to solve it like a quadratic now. Factor it out, m minus 3 times m minus 4. Set each of those factors equal to 0. And then solve each of those factors. Now, this is definitely one of those situations where I should plug in and make sure that both of these work. So if I plug in a 3 plus 12 over 3, that's 3 plus 4, that does equal 7. Plug in the 4 plus 12 over 4, that's 4 plus 3, that equals 7 again. So both of these are solutions. Okay, let's take a look at our most complicated example. Now, as with before, When you see rational expressions, each of these terms is a rational expression. So we have three rational expressions here. When we have rational expressions, we want to factor the bottoms. That's a really, really big deal. Factor the bottoms. It helps you to create your least common denominator. It helps you to get rid of these fractions. So my first step, I'm going to factor that third rational expression, that one all the way over there on the right. I factor it out and I see that every fraction has x plus 3 and or 2 as a term, as a product on the bottom of the fraction. This one here actually has them both. So that tells me that I'm going to multiply this whole equation by both 2 and x minus 3. So I want to multiply by basically all of my different factors that occur throughout the equation in the bottom. When I do that, if the fraction has the x minus 3, it cancels out the x minus 3. It only gets multiplied by the 2. If that fraction has the 2, that cancels out. It only gets multiplied by the x minus 3. If it has both the 2 and the x minus 3, like the last fraction does, then both of those get canceled away, and we really don't multiply the top by anything. Now, we just start solving it like we would any other equation. I multiply things together, I combine like terms. Here I have x squared minus 7x, so I have no constant term. That tells me that when I want to factor it, I'm just going to pull out an x. I set both of these factors equal to 0, and I get x equals 0 or x equals 7. Check them both. Plug them back in, they both work. Now, let's take a look at this classic rate problem. I see these on tests like the ACT, the MME. Standardized tests seem to always have a problem like this that you have to solve in the math section. Here's my example. Bob can paint 5 rooms in 2 hours, while Rob can paint 3 rooms in 2 hours. How long will it take them to paint 10 rooms working together? Now, this is a rate problem, which means that I want to write a rate for both Bob and Rob and add those two rates together. So Bob can paint 5 rooms in 2 hours. So I put basically the number of rooms divided by the time that it takes him to paint those rooms. So it's always the jobs divided by the time to create this rate. So Bob can paint 5 rooms in 2 hours. Rob can paint 3 rooms in 2 hours. So I can do this pretty easily no matter what numbers they give me. If they tell me that Bob can paint 5 rooms in 2 hours and Rob can paint 8 rooms in 4 hours. It doesn't matter. I'm always just going the number of rooms divided by the time. I'm creating a rate. And I set that equal to a rate for them working together. So how long will it take them to paint 10 rooms? Well, I know the number of rooms is 10, and I'm looking for how much time it's going to take. So here we have a rational equation to solve. Great example of the skill we're trying to do. And not too bad to solve for this. I'm going to go ahead, multiply by 2x. So the way I want to solve this is get rid of the fractions by multiplying by 2x. The 5 and the 3 have that 2 on the bottom, so those 2's cancel out there, but they don't have that x on the bottom. So the 5 gets multiplied by the x, the 3 gets multiplied by the x. The 10 over x has the x on the bottom, that cancels out, but it doesn't have anything to get rid of the 2, so I have to go 10 times 2 and I get 20. Add the 5x and the 3x, divide it over, and I find out that it takes Rob and Bob 2.5 hours if they work together to paint these 10 rooms. All right, so let's continue on by talking about rational inequalities. A rational inequality looks a lot like a rational equation, except it's got an inequality symbol. So instead of saying x minus 5 over x equals 2, we might have x minus 5 over x is greater than 2. So we're going to take a look at how to solve these. Obviously, it's going to be different, but similar to solving rational equations. The thing that I need to focus on is there's two different possibilities. My x, I don't know what it is. My x, which is the denominator on the bottom, could be positive or it could be negative. So I have to deal with those two possibilities. When my denominator is positive and when my denominator is negative. Now, let's go ahead and assume that my denominator is positive. So that means that when I multiply this whole inequality by x, the sign does not change. So I multiply by x, and I start to solve this inequality just like I would any other inequality. I get x is less than negative 5. I bring over the 2x, I add over the 5, and I get negative x is greater than 5, and then when I get rid of that negative, it flips it back. So if my least common denominator is positive, now I need to go back and actually deal with that. That's a statement that I made up here. I'm going to actually write another statement up here. X, my denominator, is greater than 0. So now I need to look, do these two statements work together? Okay, I made the assumption that x was positive, that x was greater than 0 when I started this problem. Now, when I get all the way down here, it says that x is less than negative 5. That does not work. X cannot be greater than 0 and less than negative 5. So this one is not possible because these two statements don't agree. So this one is not possible. Now, let's take a look at the other side of this. If my least common denominator is negative, and I forgot to change this, so we're going to do it now. If my least common denominator is negative, now when I multiply by it, I have to flip the sign. Now, when I'm saying that my least common denominator is negative, that means that x, my bottom right here, is less than 0. Now let's see if things agree when I solve it. So multiply over the x, start to solve it. I bring the 2x over, I add the 5 over, I divide by negative 1, so now my sign flips again. Now, do these two agree? Can x be less than 0? My bad. Can x be less than 0 and be greater than negative 5? Is this possible for these two to agree? Yes, it is when x is greater than 5. Excuse me, I wrote that wrong. Get my eraser. When x is greater than negative 5 and less than 0. So this only works for a very narrow band of numbers. Numbers that are greater than negative 5 but less than 0. So these two statements, the one that I create and then my solution, need to agree. All right, let's try this again with another example. Here, my least common denominator, and basically my least common denominator is just this x minus 4. Gosh darn it. Is just this x minus 4 right here. So I'm going to multiply that over and I'm going to say x minus 4 is greater than 0. Now that means that x needs to be greater than 4. I go through my process of solving this. I multiply over my x minus 4, and because I'm assuming it's positive, I do not flip this sign. I do not flip this sign right here. I leave it because I'm multiplying by a positive number. I continue solving it, and I get x is greater than or equal to 0. So can these two statements agree? X is greater than or equal to 0, and x is greater than 4. Do these two work together? And the answer is yes, but I'm just going to go with the bigger number. X has to be greater than 4, and by default, it's going to be greater than or equal to 0. Let's look at the other side of this where my denominator is negative. So that means that x minus 4 is less than 0. That means x is less than 4. Now when I multiply by that, it's going to flip my sign. So you'll notice that this sign has flipped. Get my pen here. That sign has flipped now. Go ahead and continue solving it. I get x is less than or equal to 0. Is it possible for a number to be less than 4 and less than or equal to 0? And the answer is yes, but I'm going to go with the smaller of the two numbers. If x is less than or equal to 0, it is by default less than 4. So this is my answer. Okay, so that's going to be it. It's time for you to get to work on some of these problems on your own. I'll see you in class, and I'll see you online.